Our goal with this project was to implement a robot that would be able to move forward alongside a wall while staying a certain distance from it. This is something that we did with Turtlebot 4 while simulating this robot. The way we formulated this problem is by having two inputs, one of them being a LiDAR scan, which would inform the robot of its distance from the wall, its distance from obstacles, and pretty much where it is located in terms of the wall next to it or in terms of an obstacle in front of it. It would pretty much give it the information that it needed to adjust accordingly while moving alongside the wall. It would also have an input of the odometry, which is basically what the robot's position is within the space and its orientation, whether or not it's facing the wall or away from it or slightly towards the wall. That's one of the inputs that we also had. And the output would be what the robot would do as a result of the inputs, in which direction it would have to move to maintain a 1 meter distance from the wall, which is the distance that we had the robot maintain parallel to the wall while it would move forward. And this pretty much would inform the robot of how fast it would have to move and in which direction it would have to move to maintain this distance.
So now we move on to the implementation of our project. So in the implementation phase of our project, we built a full wall following controller for the Turtlebot 4 using LiDAR sensing, a proportional derivative controller, and a logging and analysis pipeline so we could measure performance. I'll start off by showing how our code modules work together, and then explain the PD controllers and loops that drive the robot, and finally show a short demonstration of the system running. The diagram shows the overall flow of our implementation. The process begins with the wallfollower which is a ROS2 node that runs on the real time on the robot. While the robot follows a wall, the node does two things. It executes the control loop that drives the robot, and it logs important data such as LiDAR readings, computed errors, and the velocities we publish. These logs are all stored in the wallfollow log.csv, and which becomes our data set for the evaluation. After we run, we take the CSV file that it outputs and feed it into the wallfollowanalysis.py file. This analysis script calculates metrics such as distance tracking error over time, and it generates plots showing how smoothly the robot followed the wall. Finally, the results are exported into wall follow analysis PDF, which gives us the clear summary of the robot's performance that we use in our results section. The pipeline allows us not only to implement the controller, but also to measure how well it actually worked. Now I'll walk through the control loop itself, which is what keeps the robot aligned with the wall. The loop starts with LiDAR scans from the scan topic. We extract range we care about, the left, the front left, and the rear left directions. These values gives us the robot's current distance from the wall and its orientation relative to it. Next, the readings go into the sensor processing, where we filter any invalid values and smooth the data so that the controller doesn't react to small spikes. From the process data, we compute the error. The distance error is the difference between our desired distance from the wall and the measured left distance. We also compute the heading term, which is based on the difference between the front left and the rear left beams of the LiDAR. At this stage, we also append all relevant information and data to our output file for logging. The error then passes to the PD controller, which generates an angular velocity command. This proportional term corrects how far we are from the wall, and the derivative term helps smooth oscillations by responding to change in error. We also clamp the command so the robot does not turn too sharply. After that, we combine the turn command with the forward linear velocity and publish a twist message to CMD underscore velocity. The final block is motion. The robot physically moves, which changes the distance from the wall. That creates a natural feedback loop. After the robot moves, LiDAR sees new environment and the cycle repeats around 10 to 20 times per second. This closed loop process allows the robot to continuously correct itself and follow the wall smoothly. Attached is the video demonstration. Here's a short demonstration of the controller running the simulation. As you watch, notice how the robot stays roughly in the same direction from the wall and makes small corrections based on the PD controller. You'll also see how it slows slightly when approaching turns and smoothly navigates corners. Lastly, our resources for tools, we used the Gazebo simulator, Python libraries such as Matplotlib and NumPy, and ROS2. And for references, I referenced two websites, one Python PID controller example, which was really the backbone of how I was able to understand the PD controller and implement it in the project, and ROS2 documentation that allowed me to fully understand what I was doing with ROS2. Lastly, we used ChatGPT just for minor debugging and setting up the Gazebo environment, which did take a while.
Distance error versus time. This graph shows how far the robot drifted from the 1 meter mark. During cornering, it'll spike. Other than that, it should stay relatively stable. Angular command versus time. This shows the angular velocity at which the robot will change its angle to stay within the 1 meter limits given to it. That is why it spikes so much as it takes corners. Heading error versus time. The heading error oscillates around 0, showing that the robot continually turns left and makes micro adjustments to stay parallel to the wall at about 1 meter. The spikes show when it takes a corner, as it has to make drastic changes. Wall distance versus time. The wall distance remains close to the desired 1 meter, and as it takes a corner, it fluctuates, as you see within the graph. This shows that the adjustment is necessary while taking wider angles. Our wall following system for the TotalBot was a success. Implemented within a simulation, the controller maintained stable tracking of our desired wall distance and ensured collision-free navigation. Analysis of the distance, heading, and angular command data confirms consistent, reliable behavior throughout all of our runs. Some future improvements we'd like to make is dynamic obstacle detection for real-world environments. Another future improvement we'd like to look into would be adjusting the tolerances and speed, getting the robot as fast and efficient as possible. Any questions?